Hello friends, we start this lecture with the introduction of the concept of a pure substance and a discussion of the physics of phase change processes. We then illustrate the various property diagrams and PVT surfaces of pure substances. After demonstrating the use of the property tables, the hypothetical substance, ideal gas and the ideal gas equation of state shall be discussed in this and the following lectures. Pure substance. A substance that has a fixed chemical composition throughout is called a pure substance. Water, nitrogen, helium and carbon dioxide, for example, are all pure substances. A pure substance does not have to be of a single chemical element or compound, however. A mixture of various chemical elements or compounds also qualifies as a pure substance as long as the mixture is homogeneous. Air, for example, is a mixture of several gases, but it is often considered to be a pure substance because it has a uniform chemical composition. However, a mixture of oil and water is not a pure substance. Since oil is not soluble in water, it will collect on top of the water, forming two chemically dissimilar regions. A mixture of two or more phases of a pure substance is still a pure substance as long as the chemical composition of all phases is the same. A mixture of ice and liquid water, for example, is a pure substance because both phases have the same chemical composition. A mixture of liquid air and gaseous air, however, is not a pure substance since the composition of liquid air is different from the composition of gaseous air, and thus the mixture is no longer chemically homogeneous. This is due to different components in air condensing at different temperatures at a specified pressure. Phases of a pure substance. We all know from experience that substances exist in different phases at room temperature and pressure. Copper is a solid, mercury is a liquid and nitrogen is a gas. Under different conditions, each may appear in a different phase. Even though there are three principal phases, solid, liquid and gas, a substance may have several phases within a principal phase, each with a different molecular structure. Carbon, for example, may exist as graphite or diamond in the solid phase. Helium has two liquid phases. Iron has three solid phases. Ice may exist at 7 different phases at high pressure. A phase is identified as having a distinct molecular arrangement that is homogeneous throughout and separated from the others by easily identifiable boundary surfaces. The two phases of H2O in iced water represent a good example of this. When studying phases or phase changes in thermodynamics, one does not need to be concerned with the molecular structure and behavior of different phases. However, it is very helpful to have some understanding of the molecular phenomena involved in each phase. Intermolecular bonds are strongest in solids and weakest in gases. One reason is that molecules in solids are closely packed together, whereas in gases they are separated by relatively large distances. The molecules in solid are arranged in three-dimensional pattern or lattice that is repeated throughout. Because of the small distances between molecules in a solid, the attractive forces of molecules on each other are large and keep the molecules at fixed positions. The molecular spacing in the liquid phase is not much different from that of the solid phase, except the molecules are no longer at fixed positions relative to each other and they can rotate and translate freely. In a liquid, the intermolecular forces are weaker relative to solids, but still relatively strong compared with gases. The distance between molecules generally experience a slight increase as a solid turns liquid, with water being a notable exception. In gas phase, the molecules are far apart from each other and a molecular order is non-existent. Gas molecules move about at random, continually colliding with each other and the walls of the container they are in. Particularly at low densities, the intermolecular forces are very small and collisions are the only mode of interaction between the molecules. Molecules in the gas phase are at considerably higher energy level than they are in the liquid or solid phases. Therefore, the gas must release a large amount of its energy before it can condense or freeze. Compressed liquid and saturated liquid. Consider a piston cylinder device containing liquid water at 20 degrees centigrade and 1 atmosphere pressure. Under these conditions, water exists in the liquid phase and it is called a compressed liquid or a subcooled liquid, meaning that it is not about to vaporize. Heat is now transferred to the water until its temperature rises to, say, 40 degrees centigrade. As the temperature rises, the liquid water expands slightly and so its specific volume increases. To accommodate this expansion, the piston moves up slightly. The pressure in the cylinder remains constant at 1 atmosphere during this process, since it depends on the outside barometric pressure and the weight of the piston, both of which are constant. Water is still a compressed liquid at this state, since it has not started to vaporize. As more heat is transferred, the temperature keeps rising until it reaches 100 degrees centigrade. At this point, water is still a liquid, but any heat addition will cause some of the liquid to vaporize. That is, a phase change process from liquid to vapor is about to take place. A liquid that is about to vaporize is called a saturated liquid. Therefore, state 2 is a saturated liquid state. Saturated vapor and superheated vapor. Once boiling starts, the temperature stops rising until the liquid is completely vaporized. That is, the temperature will remain constant during the entire phase change process if the pressure is held constant. This can be easily verified by placing a thermometer into boiling pure water on top of a stove at sea level with pressure equal to 1 atmosphere. The thermometer will always read 100 degrees centigrade if the pan is uncovered or covered with a lid. During a boiling process, the only change we will observe is a large increase in the volume and a steady decline in the liquid level as a result of more liquid turning to vapor. Midway about the vaporization line, the cylinder contains equal amounts of liquid and vapor. As we continue transferring heat, the vaporization process continues until the last drop of liquid is vaporized. At this point, the entire cylinder is filled with vapor that is on the borderline of the liquid phase. Any heat loss from this vapor will cause some of the vapor to condense. A vapor that is about to condense is called a saturated vapor. Therefore, state 4 is a saturated vapor state. A substance at states between 2 and 4 is referred to as a saturated liquid vapor mixture, since the liquid and vapor phases coexist in equilibrium at these states. Once the phase change process is completed, we are back to a single phase region again, this time vapor, and further transfer of heat results in an increase in both the temperature and the specific volume. At state 5, the temperature of the vapor is, let us say, 300 degrees centigrade, and if we transfer some heat from the vapor, the temperature may drop somewhat, but no condensation will take place as long as the temperature remains above 100 degrees centigrade for pressure equal to 1 atmosphere. A vapor that is not about to condense, that is not a saturated vapor, is called a superheated vapor. Therefore, water at state 5 is a superheated vapor. The constant pressure phase change process is illustrated on a TV diagram in this figure. If the entire process described here is reversed by cooling the water while maintaining the pressure at the same value, the water will go back to state 1, retracing the same path, and in so doing, the amount of heat released will exactly match the amount of heat added during the heating process. In our daily life, water implies liquid water and steam implies water vapor. In thermodynamics, however, both water and steam usually mean only one thing, that is H2O. Saturation temperature and saturation pressure. It probably came as no surprise to you that water started to boil at 100 degrees centigrade. Strictly speaking, the statement water boils at 100 degrees centigrade is incorrect. The correct statement is water boils at 100 degrees centigrade at 1 atmosphere pressure. The only reason water started boiling at 100 degrees centigrade was because we held the pressure constant at 1 atmosphere or 101.325 kilopascal. If the pressure inside the cylinder were raised to 500 kilopascal by adding weights on top of the piston, water would start boiling at 151.8 degrees centigrade. That is, the temperature at which water starts boiling depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. At a given pressure, the temperature at which a pure substance changes phase is called the saturation temperature. Likewise, at a given temperature, the pressure at which a pure substance changes phase is called the saturation pressure. At a pressure of 101.325 kilopascal, T saturation is 99.97 degrees centigrade. Conversely, at a temperature of 99.97 degrees centigrade, P saturation is 101.325 kilopascal. Saturation tables that list the saturation pressure against the temperature are available for practically all substances. A partial listing of such a table for water is given in this figure. This table indicates that the pressure of water changing phase at 25 degrees centigrade must be 3.17 kilopascal and the pressure of water must be maintained at 3976 kilopascal to have it boil at 250 degrees centigrade. During a phase change process, pressure and temperature are obviously dependent properties and there is a definite relation between them, that is T saturation is equal to F into P saturation. The plot of T saturation versus P saturation is called a liquid vapor saturation curve. A curve of this kind is characteristic of all pure substances. It is clear from this plot that T saturation increases with P saturation. Thus, a substance at higher pressures boils at higher temperatures. In the kitchen, higher boiling temperatures mean shorter cooking times and energy savings. Mutton, for example, may take 1 to 2 hours to cook in a regular pan that operates at 1 atmosphere pressure, but only 20 minutes in a pressure cooker operating at 3 atmosphere absolute pressure. Corresponding boiling temperature is 134 degrees centigrade. The atmospheric pressure and thus the boiling temperature of water decreases with elevation. Therefore, it takes longer to cook at higher altitudes than it does at sea level, unless a pressure cooker is used. The variation of the boiling temperature of water with altitude at standard atmospheric conditions is given in this table. For each 1000-meter increase in elevation, the boiling temperature drops by a little over 3 degrees centigrade. Note that the atmospheric pressure at a location and thus the boiling temperature changes slightly with the weather conditions, but the corresponding change in the boiling temperature is no more than about 1 degree centigrade. Some consequences of T saturation and P saturation dependence. We mentioned earlier that a substance at a specified pressure boils at the saturation temperature corresponding to that pressure. This phenomena allows us to control the boiling temperature of a substance by simply controlling the pressure, and it has numerous applications in practice. Here we discuss some examples. Consider a sealed can of liquid refrigerant 134A in a room at 25 degrees centigrade. If the can has been in the room long enough, the temperature of the refrigerant in the can is also 25 degrees centigrade. Now, if the lid is opened slowly and some refrigerant is allowed to escape, the pressure in the can will start dropping until it reaches the atmospheric pressure. If you touch the can, you will notice its temperature dropping rapidly and even ice forming outside the can if the air is humid. A thermometer will register a temperature of 26 degrees centigrade when the pressure drops to 1 atmosphere, which is the saturation temperature of refrigerant 134A at that pressure. The temperature of the liquid refrigerant will remain at 26 degrees centigrade until the last drop of it vaporizes. Another aspect of this interesting physical phenomena is that a liquid cannot vaporize unless it absorbs energy in the amount of the latent heat of vaporization, which is 217 kilojoules per kg for refrigerant 134A at 1 atmosphere. Therefore, the rate of vaporization of the refrigerant depends on the rate of heat transfer to the can. The larger the rate of heat transfer, the higher the rate of vaporization. The rate of heat transfer to the can and thus the rate of vaporization of the refrigerant can be minimized by insulating the can heavily. In the limiting case of no heat transfer, the refrigerant will remain in the can as a liquid at 26 degrees centigrade indefinitely. Vacuum cooling. A practical way of cooling leafy vegetables is vacuum cooling, which is based on reducing the pressure of the sealed cooling chamber to the saturation pressure at the desired low temperature and evaporating some water from the products to be cooled. The heat of vaporization during evaporation is absorbed from the products, which lowers the product temperature. The saturation pressure of water at 0 degree centigrade is 0.61 kilopascal and the products can be cooled to 0 degree centigrade by lowering the pressure to this level. The cooling rate can be increased by lowering the pressure below 0.61 kilopascal, but this is not desirable because of the danger of freezing and the added cost. In vacuum cooling, there are two distinct stages. In the first stage, the product at ambient temperature, say at 25 degrees centigrade, are loaded into the chamber and the operation begins. The temperature in the chamber remains constant until the saturation pressure is reached, which is 3.17 kilopascal at 25 degree centigrade. In the second stage, saturation conditions are maintained inside a progressively lower pressures and the corresponding lower temperatures until the desired temperature is reached. So friends, here we come to the end of our discussion in today's lecture, and therefore we sum up. A substance that has a fixed chemical composition throughout is called a pure substance. In liquid phase, a substance that is not about to vaporize is called a compressed or subcooled liquid. In the gas phase, a substance that is not about to condense is called a superheated vapor. During a phase change process, the temperature and pressure of a pure substance are dependent properties. So that is it for today. In the next lecture, we shall be discussing about property diagrams. Thank you very much.